Good morning. Welcome to the session on scalable machine learning with AWS Batch. My name is Mahadevan Balasubramaniam, a principal solution architect for autonomous computing.
And I am Venkatesh Rajagopalan, also a principal solution architect for autonomous computing. In this webinar, we'll be discussing some of the scaling challenges in machine learning. We'll also be demonstrating an AWS batch-based methodology that can address some of these challenges. The presentation is organized as follows. We'll start with a discussion on computational challenges in machine learning. Then we'll talk about the implications on compute infrastructure, training strategies, algorithms, and distributed computing. We will also provide a brief overview of AWS Batch and discuss some of its constructs and features. Next, we'll show a demonstration where we leverage AWS Batch for solving an unsupervised machine learning problem at scale. And we'll be glad to answer any questions, if any, at the end of this presentation. In this slide, we list some of the computational challenges in machine learning. The first and foremost challenge is that machine learning, and in particular deep learning models, are getting bigger and bigger. For example, natural language processing models have gone from having hundreds of millions of parameters in 2018 to having hundreds of billions of parameters in 2020, as you can see in the chart shown in the slide. The second challenge is scale. Even if a model is not particularly complex, customers might want to build thousands of such models simultaneously and select the best. They might want to search over architectures and hyperparameters to define the best model for the business outcome. Finally, there are some downstream applications of machine learning, such as sensitivity analysis and uncertainty quantification, which may require millions of model evaluations as well. To address the challenge of training large deep learning models, hardware acceleration is critical. We have powerful GPUs like the NVIDIA A100 and multi-GPU nodes like P4D that have 8 A100 GPUs. In addition to the GPUs, faster connections between GPUs and technologies like the Elastic Fabric Adapter, which provides about 400 gigabits per second of network bandwidth, are critical. Another way to efficiently train large models is to use strategies like data parallelism and model parallelism. We can also use techniques like ring-all reduce. This technique reduces the amount of time spent communicating between different GPUs, allowing them to spend more time doing useful computation. What about the other challenges? For the other two challenges, that is building a large number of models and downstream applications, algorithm redesign coupled with distributed computing can be very effective. For example, in architecture search, all model training tasks can be executed in parallel. In the case of hyperparameter tuning, say you're using genetic algorithms for that, the genetic algorithm can be adapted for a distributed computing environment. For such tasks which are embarrassingly parallel, AWS Batch can be leveraged. In the demonstration, we'll showcase a batch-based methodology to solve an unsupervised machine learning problem at scale. But prior to that, Mahadevan will provide an overview of AWS Batch.
Thanks, Venkatesh, for the introduction. In this section, I will provide an overview of AWS Batch along with its features that would help us address scalable machine learning. So, what is AWS Batch? AWS Batch was launched in 2017 with the objective of streamlined running of workloads in the cloud. It comprises of two main entities. It has a job scheduler and an orchestrator. The job scheduler controls and manages the job lifecycle for millions of jobs, from managing its dependency and also retry the jobs, and also have a way of monitoring the states of the jobs. The orchestrator is a fully managed service that would help you to run your containerized application. So all you need is a Docker command, a Docker container image, and the parameters with which you would like to run that Docker image. So the batch would evaluate when, where, and how to run the jobs that have been submitted in a job queue. It would provision and scale the compute instances that is needed for the job queue, and then shut them down when the job is completed. Overall, it manages the job queues and the workflow from start to finish, and can even address a different mix of hardware requirements where some of your tasks would need a CPU intensive compute, while the others would need a GPU intensive compute. So why do we need AWS Batch? AWS Batch has been constantly evolving to give you the ability to choose a solution that works best for your workload. Batch will help to provision appropriate resources for your jobs, manage, monitor, and scale for your entire set of jobs. AWS Batch maintains the job, its dependency, and also manages its retry lifecycle, so that you would be able to retry jobs that failed and get it to a successful state so that your overall process would run successfully. AWS Batch also provides seamless integration with other AWS services such as Lambda, Step Functions, DynamoDB, and S3. Batch also dynamically provisions an optimal quantity and the type of compute that is needed for the job. And it does that based on the volume of the jobs and the specific resource requirements that have been specified while the jobs have been launched. And finally, it is cost efficient because AWS Batch is free. We only pay for the AWS resources such as the instances, S3, and the DynamoDB that gets used by the jobs. In summary, the batch takes care of all the heavy lifting so that we as users could focus on applications like shell scripts, executables, containers, and the resource requirements, and batch will take care of the rest. From a distributed ML perspective, if we have a lots of jobs, say millions, it is not viable to submit one job at a time. Instead of submitting a large number of independent single jobs, Batch also supports a feature called array jobs, where you could give a command that you would like to run and run 1,000 copies of this one over the entire set of data. So that each job can do effectively the same thing, but working on part of the data And with this, we would be able to solve the much bigger puzzle and assemble them later so that we can get the entire benefit of running a massively parallel job. Given this construct, array jobs are an efficient way to run large parametric sweeps and Monte Carlo simulations, and it works excessively well for the case where we want to run embarrassingly parallel workloads. So batch provides a way for managing the dependency between the jobs. Here, an array job is represented by a larger box with several of its sub, which are shown by smaller rectangles within that. So job A is made up of 100 jobs which have index from A0 to A99. So in terms of dependency between the jobs, batch provides several constructs. In this case, job A is an array job and job B is a single job. So in this dependency, job B would start only when all of the candidates of job A has been completed. On the second note, we could start an array job based on a successful completion of a prior job, as you see over here, where job A has to complete before the array job B starts to run. Batch also provides for an ability for two equally sized jobs, where you have a job A of size n, which is followed by a job B of size n. We could have an n to n dependency, where as soon as the 0th index job gets completed, the 0th index of the following job would start, as is indicated by A0, when upon its completion would result in B0 to start and continue. And finally, we also have a case where the array job depends on itself. It is aka, or very similar to a sequential job, where you want to run job 0, 1 all the way till the end in sequence. So all these different ways of having dependency between the jobs would help us to orchestrate the different jobs that are needed to achieve our scale when we are applying it on machine learning problems. Batch also accepts jobs based on the number of GPUs it requires and assigns it to compute instances that can provide for P or G family instances accordingly. While processing jobs that need a GPU, batch would pin the GPU to the container so that it prevents oversubscription of this GPU by any other job. As batch is constantly evolving, it will adopt new accelerators and GPU as they are released. Finally, batch has an excellent integration into the use of spot instances from EC2. Spot instances are spare EC2 compute capacity that offers up to a 90% discount over on-demand. Spot instances offer the same features that we are used to with EC2, but for a fraction of the cost. So the way in which we can think about spot instances is it will help us unlock the full value of EC2. So with spot, we could not only consider it as a savings mechanism, but we can also use it as a way to do more with less. In terms of the setup of the problem, we would still push jobs into a queue. The queue would be pointing to a mixture of on-demand and spot instances. So, so we have entire control on what instances the job is going to run in this particular queue. So as a result, we would not have to change anything in our code, and batch would take care of using and completing the jobs on the spot instances as and when it becomes available on EC2. With this, I will pass it on to Venkatesh, who would introduce the machine learning problem and how we would apply AWS Batch to address its scale.
Thank you, Mahadevan. In this demonstration, we will be leveraging AWS Batch to solve an unsupervised machine learning problem. In particular, we are trying to perform clustering in a high dimensional space. Our objective is to identify clusters in the fashion MNIST data. This dataset consists of images of apparels and other accessories. Some sample images are shown in the slide. For the demo, we will use 20,000 images from the dataset. Each image is of size 28 cross 28 pixels. And you can think of each pixel as a dimension. Therefore, this dataset has a dimension of 784. So what are the challenges? The first challenge is the dimensionality of the data itself, which is 784 in number. The second challenge is that we don't know the number of clusters in the data a priori. Any technique that we use should determine the number of clusters in the data by itself. Finally, the clusters formed should be robust to variations in data. The clusters should be homogeneous in the sense that a cluster should contain elements which are similar to each other, and the clusters should be differentiated as well from one another. So how do we solve this problem? To begin with, we'll use a technique called UMAP, which stands for Unified Manifold Approximation and Projection, to reduce the dimensionality of data from say 784 to a tractable number like 10 or 20. Then we'll use dbScan, which is a density-based spatial clustering technique, to find the unknown number of clusters in the data. But what are the optimal parameters for UMAP and dbScan? And how do we determine that? To identify the optimal parameters for UMAP and dbScan algorithms, we'll use a genetic algorithm-based optimization. And to accelerate the computation, we'll use the CUDA ML libraries from NVIDIA for UMAP and dbScan, which provides for GPU acceleration. And just to give you an idea of the complexity of the problem, if you were to use the standard genetic algorithm ASUS, that is with no parallelism, this task would have taken us approximately 56 hours. Each model evaluation in this case takes about 40 seconds on a P4D instance. It takes about 3 minutes on a G4D instance, on a single GPU, of course. Each generation in the genetic algorithm consists of 100 candidates. And the population evolves over 50 generations to find the optimal solution. So all these takes about 56 hours. So in order to reduce the computation time and also to leverage the power of batch, we need to redesign the genetic algorithm for batch execution. And for that, we'll split the genetic algorithm into its atomic steps, execute each atomic step either as a single job or as an array job, and do this over several generations to get to the optimal solution. To start with, we have a job that creates the initial population. This is a single job. And in our case, the initial population consists of about 100 candidates. Then we need to evaluate each member of this population, that is each candidate. And for that, we'll deploy an array job. So you have a single job followed by an array job, and the array job, which is evaluating the population, is dependent on the initial job. So it will execute only after the initial job is complete. So all these jobs will be dependent on something being complete previously and will execute only when the previous job is complete. Okay. So once all the candidates in the initial population has been evaluated, we use that to create parents, which is again a single job. And from these parents, we create offsprings. This is also a single job. Now we evaluate all the offsprings. And this job will be executed as an array job. So 100 jobs would be run in parallel. And then once the offsprings have been evaluated, we create the next generation through a single job. And this process will continue till we reach the final generation. And once we get to the end of the last generation, the job will execute. Now for each of these jobs, we would specify the dependencies, and batch will ensure that a particular job is executed only after the dependent job is complete or the dependency is complete. And for the whole process, we'll maintain the status in DynamoDB.
Thanks, Venkatesh. In the demo walkthrough, we will first show a couple of screenshots to highlight what to look for in the demo, and then go through different snippets that show the phases of the entire execution of this genetic algorithm in optimizing the parameters for this fashion MNIST data. First, this is an AWS batch dashboard that provides a view of the different queues and the jobs and its different states that exist in the queue. We could dive deep into a particular job by just clicking on the hyperlink and get to know the parameters for the job, how it was started, and how it is going to execute, and what other jobs it is dependent on, all from a unified dashboard. In addition, we would also be able to observe the compute environment that would monitor the EC2 instances that are being launched as a part of processing the jobs in the queue. Here, at one snapshot, you could see several P4D 24XLs have been spun up to process the array job. And as the task proceeds to the next one, the management of the EC2 instances is taken care where by batch, where it sunsets some of the instances and starts up new instances as the needs of the jobs evolve as it gets processed in the queue. And in addition, the queue dashboard here also shows the different jobs and its status as whether it is successful and when this particular job was started and when it was stopped, along with the total runtime for each of the jobs. As Venkatesh pointed out, we had to split the genetic algorithm so that we could leverage the scale by using a combination of AWS services like Batch and DynamoDB. From the DynamoDB, typically the details of the workload are saved in a database like DynamoDB. In order to take full advantage of the parallel scalability, we stored the internal state of the GA algorithm also into a separate DynamoDB table. This was done to facilitate rapid parallel logging as the algorithm is executed and allows for post-processing the results after the parallel execution is complete. We also have a layer in DynamoDB where the internal states of the algorithm as it goes through the different steps that Venkatesh described, they are also stored inside DynamoDB instead of being stored as flat text files, which are very limiting because it can affect the I/O during execution and post-processing that becomes cumbersome. DynamoDB integration with Batch was fully leveraged to achieve scale in this implementation. Therefore, this implementation requires a deep understanding of how algorithms work and how it can be efficiently split so that we can leverage the compute and the storage to scale horizontally. In the next set of charts, we would walk you through the snippets of the execution of the different phases of the demo. First, we will start off with a snippet to show how batch jobs are being launched from your shell. First, we build the container using the build.sh script where the container is built. We tag the container so that it could be pushed into ECR. And then we trigger the push into the Elastic Container Registry. Subsequently, we log into the container so that we could launch the jobs for starting the genetic algorithm optimization. This is done using Boto3, and the jobs are launched in a sequence as generation 0, generation 1, 2, 3, etc., till the number of generations you would like to accomplish. And so this can be effectively done in an automated way using Boto3 plus Python. In this snippet, we will show how jobs start in the compute environment through the batch dashboard. So the batch dashboard provides a view into the different queues along with the compute environment that is there. We could go into a particular job in a queue and look at the details of the job. So if I click on the pending 31 jobs that are remaining and sort by their creation order, we could see the sequence in which these jobs were created by the Boto 3 launch that we showed in the previous step. All these jobs are waiting for its prior dependency to be complete before being taken on. So the batch eval is an array job which has 50 jobs inside it. At this point, the resources are in a runnable state and it was waiting for the compute environment to become available. Now that it is available, it has entered a starting phase, and upon refresh, this task is completed and the successful state is 1. We could enter the flag based on successful and look at the details of when this job was started and when it got completed, and dive into full details about the execution of the job. We can look at the parameters that is needed to run this particular job, and more importantly, access the logs of the job that get automatically logged in CloudWatch. So this is the log where we had created the DynamoDB tables and also inserted the records into them so that the next step in the process could start. With this, the next job could start to execute because its dependency is satisfied, and the array job would start to execute. What we show here is an interim state where we have proceeded further along, where 2 jobs have succeeded. That is shown by the number of succeeded jobs. We can dive into the details of the jobs that have succeeded and look into the array job along with the following job, which was also completed in this case. So these are the details of the array jobs which have been completed, and one could monitor its log on CloudWatch. This shows the entire console output from that particular run, where the runs were performed on a P4 instance, the metrics were calculated and uploaded back into DynamoDB. Now, we are almost near the end of the run, where we have completed nearly 30 out of the 32 jobs that were launched, as is shown over here. We have completed 30 jobs successfully, and there are still 2 more jobs that are pending to be complete for the entire optimization. Next, we show the final completion of the jobs. This shows that all the 32 jobs that were launched were successful and there were no failures. We click on the jobs, the successful jobs, and look at the last generation which got completed, and this was the sequence in which these jobs were executed. Finally, after running through this GA optimization, we have complete access to all the generations that we would be able to extract from DynamoDB, slice and dice the data to analyze the results. In summary, we were able to explore nearly 5,000 potential solutions and evolved towards an optimal solution. The rendering of the robust cluster is shown in this figure, where the different colors indicate the clusters. We achieved this within an hour as compared to the original estimate of 56 hours if it were to be launched sequentially. Therefore, we are able to compress the execution time by as much as 50x because of AWS Batch. In summary, we discussed about the computational challenges in machine learning. We also described a methodology leveraging AWS Batch to address these challenges. Finally, we demonstrated this on an unsupervised learning problem. We encourage you to explore AWS Batch to address your machine learning needs. Thank you.